All right, so today we're going to talk about arc length. All right, so there are times when we need to find the length of a graph on a certain interval. In order to estimate the length, what we can do is we can divide up that arc length into several subintervals. All right, and then what we can do, so just think about it. So I'm not going to read what it says there, but essentially, if I want to do this, right, what I can do is I can just add up all this individual lengths. All right, so if I add up all these individual lengths, which are on this table over here, and again, you don't have to necessarily worry about the table for now, but in order for me to get an approximation of the length of that arc, what I would do is add each individual length, and in this case, I'm going up by intervals of a half. Right, so to find that length, what I can do is notice that if I do it like this, right? If I just figure out the change in x and the change in y, then I can use a Pythagorean theorem where this little interval right here, this line, this length of this line is the same thing as the square root of delta x squared plus delta y squared. All right, and when I say delta x and delta y, I mean the change in x and the change in y. Okay, so, and that's all that's happening right here, right? So, for example, this right here, how I found that length is that I went back to it. I went back to the first set of numbers, and then I did 0.5 minus 0, then I did 3.125 minus 4, and this is how I got those numbers. I square them, take the square root, and that's how I figure out that length, right? And if I add all these lengths, I get an approximation the approximate length of this curve right here for this function. Okay, now let's say that we're trying to find the exact length of the curve, right? How can I possibly get a better approximation, if you will, or the exact length of the curve? Well, what we can do is we can have an infinite amount of little sections of lines, all right? So I can have an infinite amount of little lines. So what I mean by that is that I could probably go back over here and just make several tiny little lines, right? And if I make the length of the line infinitely small, okay, then I can, and then if I add all those little pieces together, then what I get is the exact length of the curve, right? So notice what I'm saying. I'm saying to take a bunch of infinitely small lines, and I'm asking you to add all those infinitely small lines, and you would have the exact, the exact length of the curve. And what that should sound to you, it should sound to you like calculus, right? So we're actually going to do some calculus to figure out the exact length of an arc. All right, so there's a couple of things you have to know. For example, that you have to assume that f is a smooth function. All right, and of course you have to have an interval, like they have to give an interval, and the derivative has to be continuous. So again, it has to be a smooth curve for you to be able to even do this. All right, so let's go ahead and derive the formula here. So again, remember what I said, right? To derive the formula, we have to make a bunch of small lines. So let's pretend that where I have those dots, those 2 points are so infinitely close that I have an infinite amount of lines in here. All right, so what I would do here is that for me to find this, all right, we can actually zoom in here. All right, so I guess I'll change that to green here just for fun. Let's say that I'm looking for this line, right? So I'm going to call that length dl, an infinitely small length. So I'm going to come over here, I'm going to zoom in. And when I zoom in, what I can do is that little distance right there, which I call dl. In order for me to find that, instead of just writing the change in x and the change in y, in this case, I would find the infinitely small length in x and the infinitely small length in y. Okay? So now, if I'm trying to find dl, or that distance right there, so dl is going to be equal, and let's call L, by the way, the arc length. Okay. So dl would be the square root, kind of like I said earlier, of dx squared plus dy squared. Okay. So that just gives me the length of the small line. But if I want to get the arc length, all right, what I would have to do is I would have to integrate the left and the right. So I integrate the left side, I would end up with the length is equal to the integral of dx squared plus dy squared. Okay? Now, what I'm going to have to do here is I have to do a little bit of math because this is not really a formula that I can use. All right, so what I'm going to do now is I'm going to factor out a dx squared. All right, so again, I'm going to factor out a dx squared. Excuse me, I wrote dt for some reason. And that is going to give me 1 plus, I can actually write it like this. Okay, so at that point, that's what I have. All right, now this one may not make some sense to you, but if you distribute the dx squared, you'll see that I am telling you the truth. Okay, so now what I can do is when I'm taking the square root, and again, remember that I should probably put this in parentheses. This is dx squared, all right, times 1 plus dy over dx squared. When I take the square root, I'm going to take the square root of each individual one. So when I do that, I'm going to leave this on the inside. And then dx, the square root of dx squared is dx. So I'm able to take the dx out of the square root, okay? So notice that now what I have here is if I just find the integral between a and b in this case, right, if I add up all the single little lengths, that this is the formula that I need. So that's the formula. Now, I simply were to write that, and that's normally the way that I'm going to write it, which really doesn't make a difference, is I can write this as 1 plus f prime of x and, of course, square all of that. Okay. So this is the formula that we need, right? So that's the formula that we're going to be using the entire time. So up to this point, we're just trying to derive the formula, right? So hopefully that makes sense to you. Okay, so now we're going to use that formula right here to figure out the length of the curve that you see here over the interval. All right, so again, they have to keep the interval. So first, what I have to do, so the actual application of it, though the algebra can get a little difficult, it's actually not very hard to apply. All right, so I'm going to take the derivative of this. Notice that the 4 squared to 2 over 3, that's just a constant. So I'm going to leave that alone. And now I'm going to multiply this times 3/2. Because I'm going to bring the power down, subtract 1 from the power. And I guess mine is 0, so I'm just going to leave that out. Now, let's see if I simplify this, that's going to cancel this. This is going to give me a 2 over here. So that's going to be 2 squared to 2 times x to the 1/2. Which, since x to the 1/2 is the same thing as the square root of x, I can actually rewrite this as 2 square roots of 2 times x. All of that inside the square root. All right, so now I'm going to use the formula, right? So I know that the length is the integral, in this case, between 0 and 1 of this right here, of the derivative squared dx. All right, so let's simplify. 2 squared is 4. And then square roots of 2x squared is just 2x. So this is 4 times 2x, which I'm going to go ahead and just write as 8x. And really, after that, the hard part, if you're not using the calculator, is to actually figure out how to take the integral of this. Okay, so as I look at it, I always try to use substitution when it comes to this because sometimes it's easy. Now, in this case, u substitution will work, right? So I'm going to call u to be 1 plus 8x, and du is going to be 8 dx. I don't have an 8 there, so I'm going to divide that out. And while I'm at it, because I don't want to plug it back in, I just want to evaluate it. I'm going to say that if x was 1, then u, if I plug in this x back in here, remember, all right, that would give me 8 times 1 is 8 plus 1 is 9. And if I plug in the 0 back into u, 1 plus 0 is 0. Excuse me, 1. So now I'm going to rewrite this as 1 over 8, integral between 1 and 9 of u to the 1/2 du. All right, so this right here is going to be 1/8. If I add 1 to the power and divide by the same, this is 2/3. This is u to the 3/2. And I'm going to evaluate that between those two. Right, so after that, really is just a matter of algebra. Let's see, that's a 4. So we have 1 over 12. If I plug in a 9, so that's going to give me 9 to the 3/2 power minus 1 to the 3/2 power. Well, this is just going to be 1. So let's see, 9 to the 3/2 power, that's 3. 3 cubed is 27. So we have 27 minus 1, which is 26 over 12, which is 13 over 6. And that's all. So remember, what we just found is the arc length of this crazy function over here over the interval between 0 and 1. That's what we found, okay? So let's go ahead and go to example number 2. All right, so same thing. I'm going to go a little bit faster here. Not much, but just a little bit. So first, remember, I got to take the derivative. And for that, I have to use the chain rule. All right, that's obviously going to cancel, so that's going to leave me with 2x times the square root of x squared plus 1. All right, so now the formula says the length is the integral between 0 and 3 in this case of the square root of 1 plus the derivative squared. In this case, the derivative is 2x times the square root of x squared plus 1. All of that squared dx. Okay. Okay, so let's just simplify at this point. That would give me 0, 3 here. This is still going to be 1. So this is 1. That's going to be 4x squared times x squared plus 1 dx. Let's see, if I distribute that 4x squared, that's going to give me 4x to the 4th plus 4x squared, and then the 1 that's from here. Okay, and I have the square root. Now, in this case, again, the hard part sometimes is doing this part. It's definitely not use substitution in this case, but I've noticed that I can factor. All right, so when you factor this, you'll realize that the factors are 2x squared plus 1 times 2x squared plus 1, which makes it 2x squared plus 1 squared. All right, and when I take the square root of that, and that's going to give me, so I came to this side over here, that's going to give me just the inside, 2x squared plus 1 dx. Take the antiderivative. plug in the 0 and 3, and then figure out the rest. All right, so that would be 27. Let's see, that's 18, excuse me, plus 3 minus 0, because everything else is going to go to 0. So this is going to be 21. So again, what we just found is the arc length of this curve between 0 and 3. All right, so example number 3, we're going to actually use the calculator. So really, this is not going to be that big of a deal. The only thing we have to do by hand is we have to actually take the derivative. So again, I'm going to bring that 2/3 down, subtract 1 from the power. And then I'm going to plug it into the arc length formula. And you can keep simplifying that if you want to, but otherwise, if it has a calculator, just go ahead and plug it in. And this one's going to be approximately, remember, if you're using the 84, what I mean by that is, I believe it's math number 9 if you're using the 84. All right, so that's it for that. Now, in example number 4, we are not going to use the calculator, so it's going to take just a little bit longer. So let's see, we have, all right, so in this case, the only difference is that this is a x function, all right? So all this stuff is related to y, which is fine. You're going to take the derivative as you normally would. So this is x prime is equal to, let's see, if I bring the 3 down, that would be 3y squared over 6, or 1/2 y squared. And on this side, I would have 1/2. 1/2 is just a constant, right? So FYI, this is 1/2. 1/2. I can write it like this: 1/2 to the -1. So that's what I'm going to do here. So I'm going to subtract 1 from the power. Bring the negative down, subtract 1 from the power. So that's going to give me y to the -2. So the length is going to be equal to the integral between 2 and 3 times the square root, the integral between 2 and 3 of the square root of 1 plus, I'm going to write this as y squared over 2 minus 1 over 2 y squared. Notice the y squared is on the bottom, not the top, of that square dy. Now, because I do have to do this by hand, I'm going to go ahead and expand this right here. So I have to FOIL that, right? So I'm going to FOIL it right here. So I'm going to take a little side note. When I FOIL this, I should get y to the 4th over 4 minus 1/4 minus 1/4 plus 1 over 4 y to the 4th. Again, please note that I am foiling what I just underlined. Okay, so I'm pretty sure that's right. Check it. And hopefully it'll work out. So let's see. Okay, so now, let's see, we're going to add like terms. This is y to the 4th over 4 minus 1/2 plus 1 over 4 y to the 4th. All right, so now I am going to go ahead and put this back in the formula. I'm going to add like terms. Now, the only thing to note is that right here at this point, I'm going to find a common denominator, right? My common denominator would be 4y to the fourth. And again, at that point, it's because I don't know what else to do. But this turns out is going to work out. So let's see. The y to the fourth, I'm going to have to multiply times y to the fourth, so that's y to the eighth. The 2, I have to multiply times 2y to the fourth. So this is 2y to the fourth. And let's see, at the end, the plus 1, I don't do anything to it, so because it already has a common denominator. All over 4y to the fourth. All right, so all of this is inside the square root. All right. Now, if I factor the top, I would find out that this is a perfect squared. So y to the fourth plus 1 squared would be those two factors, right? On the bottom I have this. So I guess I can rewrite it like this. I can rewrite the 4y to the fourth as 2y squared, all of that squared, which will allow me then to just write it as y to the fourth plus 1 all over 2y squared dy, which then would allow me to separate this. Right, so y to the fourth divided by 2y to the second. So remember what I'm doing here. I'm not doing anything fancy. I'm just dividing each one of those like that. This would be y to the second over 2 plus 1 over 2 y to the second dy. So I don't know. I don't know if I should rewrite that or not. I guess I could put the 1/2 on the outside, but let's not. You can integrate that now. Okay. So now, let's see. That would give me y to the third. When I divide that by 3, that would be a 6 here. And this one, if I add 1, well, that's going to give me a y to the negative 1 over negative 1. So that's going to make the negative 1/2 y to the negative 1, or that. 2 and 3, and after that, it's just a matter of doing the math here. Right, so hopefully you don't find that too bad for you. There is a couple of examples that I found at Khan Academy, just proving the formula. So if you have any more trouble understanding where this formula came from, I'll try to attach that in Google Classroom, all right? All right, well, that's it, guys. Again, hopefully not too rough, and I think this is probably one of the easiest one we've done so far.